Welcome back to the Intelligent Founder AI podcast.
Before we begin, I hope you're enjoying this series, Build versus Buy versus Rent, the AI infrastructure decision tree for startups. This is episode 8 of 9 with one final episode coming next week. This series is about helping founders make better AI infrastructure decisions before those choices become expensive, difficult to reverse technical commitments. We have been looking at when to build capability in-house, when to buy specialist tools, when to rent cloud infrastructure, and how choices around models, compute, data, deployment, and operational ownership affect both product strategy and unit economics. So, why should you care? Well, because infrastructure is no longer just a technical implementation detail. For AI startups, it can determine how quickly you ship, what margins you can sustain, whether you can meet customer requirements, and how much operational complexity your business takes on as it grows. Today's question sits directly within that framework. Where should your AI workloads run, and what does that decision make possible, or make harder? In this episode, we are leaving the data center and going to where the data actually lives. Factories, railways, aircraft, shop floors, utilities, warehouses, and other real-world environments. The question is simple. When should AI run at the edge, close to the data source, rather than in a central cloud? For founders building software for physical environments, this is not a minor infrastructure choice. It shapes product reliability, latency, data governance, operating cost, and ultimately whether a deployment works in the customer's real operating conditions. The important shift is not that AI is abandoning the cloud. It is that inference is becoming a workload placement decision. Some tasks belong in large central data centers. Some need to run on-site. Many are best handled through a hybrid architecture where local systems make time-sensitive decisions and the cloud supports training, fleet management, long-term storage, cross-site analysis, and more computationally intensive workflows. That distinction matters if you are building for manufacturing, transport, logistics, energy, agriculture, retail, construction, healthcare facilities, or any setting with cameras, sensors, machinery, vehicles, or constrained connectivity. For these applications, cloud first is not always the right default. Let's start with the economics. Cloud inference is mainly an operating expense model. You pay for compute, requests, tokens, storage, data transfer, or some combination of those things. That is extremely useful when demand is uncertain, deployment is early, or workloads are occasional. But the picture changes when you have persistent, high-volume data being generated at many physical sites. Think of a network of cameras inspecting production lines, sensors monitoring rotating equipment, or local systems processing video in retail locations. Sending every event, image, sensor window, or video stream to the cloud can create recurring costs in compute and bandwidth. It can also introduce operational dependencies that are easy to overlook in a prototype. Edge AI changes the shape of that cost base. Instead of paying for every inference forever, you buy and operate local compute. That means upfront hardware cost, electricity, enclosure design, thermal management, remote monitoring, software updates, maintenance, and eventual replacement. So Edge is not automatically cheaper. But when a workload is high volume, steady, and local by nature, the economics can become attractive because the cost of local hardware is spread across a large number of inferences over several years. The right comparison is not cloud versus edge in the abstract. It is, what does this exact workload cost over its operating life, including hardware, connectivity, cloud usage, maintenance, support, security, and downtime risk? That is the calculation founders should make before committing to an architecture. The second reason to use edge inference is latency. If a model is helping a person write an email, a few hundred milliseconds may not matter much. If it is detecting a safety event near moving machinery, guiding a robot, monitoring a live process, supporting a driver assistance workflow, or triggering a local alarm, response time can become part of the product requirement. The key point is that latency must be measured end-to-end. It is not just model inference time. It includes sensor capture, pre-processing, network transit, queuing, the model itself, decision logic, and whatever action follows. A local device can remove the network round trip and make response times more predictable. That matters most when connectivity is variable, when an action has to happen immediately, or when the system cannot safely depend on a remote service being available. But latency is only one part of the decision. The third driver is data governance. Many real-world AI products deal with sensitive operational data, video of workers or customers, infrastructure data, production information, healthcare records, location data, or commercially sensitive process information. Sometimes that data can be sent to a cloud platform with the right controls. Sometimes the customer does not want that. Sometimes a regulatory, contractual, security, or sovereignty requirement makes local processing the more practical option. Edge inference can allow an organization to process data locally and send only the minimum necessary output upstream: an alert, a count, a model score, a compressed event record, or anonymized metadata. That can reduce bandwidth requirements and give customers greater control over what leaves the site. The fourth driver is resilience. Cloud systems are powerful, scalable, and often the right choice, but physical environments do not always have reliable connectivity. Think about remote infrastructure, rail corridors, offshore sites, underground locations, aircraft, temporary work sites, or industrial facilities with constrained networks. If the product must continue working through a network outage, local inference is not a performance optimization. It is part of the resilience architecture. Now, none of this means every startup should buy edge hardware on day one. Cloud remains the right place for many jobs. Model training, experimentation, central data analysis, large-scale batch processing, fleet-level optimization, and workloads with unpredictable demand. The most practical architecture is often hybrid. Run immediate, repeatable, privacy-sensitive, or connectivity-critical tasks locally. Send selected data and events to the cloud for model improvement, cross-site learning, dashboards, central coordination, and tasks that genuinely need larger compute resources. The hardware landscape is making local AI more practical. Compact systems now provide enough capability for serious computer vision, sensor fusion, anomaly detection, lightweight language models, and local automation. NVIDIA's Jetson range, for example, spans small, power-constrained edge devices through to more capable systems for robotics and industrial AI. Desk-side AI systems also show how much local development, prototyping, and experimentation can now happen outside a traditional data center environment. But hardware capability is only one part of the deployment. A successful edge product also needs robust model optimization, power and thermal design, remote observability, secure software updates, device identity, offline behavior, failure handling, and a realistic support model. This is where many software-first founders underestimate the challenge. You are no longer deploying only to browsers and cloud servers. You are operating a distributed fleet of physical systems in environments you do not fully control. So here is a practical decision framework. Ask 4 questions. First, does the application need a guaranteed low latency response in the real environment? Second, does it generate enough local data or inference volume that cloud compute and data transfer become a material operating cost? Third, does the data need to remain on site because of privacy, security, commercial sensitivity, or regulatory requirements? Fourth, must the system continue operating when connectivity is limited, degraded, or absent? If the answer is yes to one of these, edge may be worth assessing. If the answer is yes to several, edge or hybrid deployment should be part of the product architecture from the beginning, not treated as a later optimization. The real lesson is not always run AI at the edge, and it is this: put each workload where it can meet its requirements for speed, resilience, cost, privacy, and operational control. For many physical AI products, that will mean local inference for immediate decisions and cloud infrastructure for learning, coordination, and scale. That is the edge AI question founders need to answer early, before a cloud-first prototype becomes an architecture that cannot survive contact with the real world. This was the Intelligent Founder AI podcast. If today's episode sparked an idea for a product that cannot live entirely in a browser tab, write it down and send this episode to the builder you would most like to work on it with. Subscribe to Intelligent Founder AI for more deep dives into AI infrastructure, edge systems, and the decisions that shape practical deep tech products. And join me next week for the final episode in the Build versus Buy versus Rent series. See you in the next episode.